Welcome back, students. This is Module 2.2.3, Passive Processes, Osmosis. Osmosis is a subset of diffusion. Diffusion and osmosis both belong to the set of transport processes that we call passive because neither requires an input of energy. Both utilize the energy that's in a concentration gradient. As I said, osmosis is a special case of diffusion. Osmosis is defined as the diffusion of water across a semi-permeable membrane. So the movement of water from an area of higher concentration on one side of a membrane to an area of lower concentration on the other side of a membrane. The word semi-permeable means penetrable by some things and not by others. Allows some particles to pass while preventing others. Consider this. If the solutes in a solution are prevented from crossing a membrane, but the water molecules can, this creates a unique situation which requires you to think about it just slightly differently. The water molecules will tend to move to the side of the membrane that has a higher concentration of solutes. As this illustration shows, this endows osmosis with the ability to do some work. If we look at the beaker on the top, which would be time 1, T1, we can see solution A and solution B have equal volumes, but solution B is more concentrated. In the same volume, it has a higher concentration of solute molecules, the little green spheres, while solution A has the same volume of solvent, but has fewer solutes. And therefore, this is a situation because they are separated by a membrane. In this case, it would probably be an artificial membrane, maybe some dialysis tubing, but here they've just labeled it as a lipid bilayer. And the water is going to move from where there's more water to where there's less water. And because the volumes are the same and there's fewer solutes here, therefore there's more water. Over here in solution B, there's the same volume of water, but there's more solutes, so there's less water. Therefore, water is going to move from where there's a higher concentration in solution A to solution B. And as it does so, it moves across the membrane by osmosis, and it moves upward against gravity. And this is actually a force which is being exerted by osmosis. It's called osmotic pressure. And so it does have this inherent force within it. We can see a second example. This really isn't that good. This is just simple diffusion, but in this case we could say that it's water molecules. If we look at this scenario, in this case we have a lipid bilayer in the center. You can see the little fatty acid tails and the phosphate heads there, the hydrophilic regions on the outside and the hydrophobic on the inside. And then we can see water on both sides, and it looks like there's about the same amount of water. The water are the little blue and molecules with the small hydrogens there. The green represents the solutes that are here. And we can see on the right side that there are more solutes than on the left side. So this is more concentrated in terms of solutes. But because there's a higher concentration of solutes, there's a lower concentration of water on the right side. On the left side, because there is a lower concentration of solutes, there's a higher concentration of water, which is the solvent. Therefore, water will move from an area of higher concentration of water to a lesser concentration of water. So water will move by osmosis from left to right. It's almost as though the water is trying to dilute the solutes so that there is an equilibrium there. But this is not typically possible in the cases that we see. Now, there are three terms that we use to describe different osmotic concentrations. The first term is hypertonic. A hypertonic solution, let's look at the etymology of hypertonic before we look at the definition. Hyper means a high level, and tonic means concentration. So this is a highly concentrated solution. But remember, these definitions are all relative. They compare one solution to another. So a hypertonic solution is a solution that has a higher concentration of solutes than another solution. And the second solution must be specified. The second term we use to describe different osmotic situations is the term hypotonic. Hypo means low. Think of hypoglycemic, which means low sugar, as in low blood sugar. In this case, hypotonic means low concentration. So a hypotonic solution is a solution that has a lower concentration of solutes than another solution. The third term is isotonic. Iso means the same, and this refers to the only other possibility. You can either have a solution that's more concentrated, a solution that is less concentrated or hypotonic, or it can be equally concentrated, and that's what the term isotonic describes, an equally concentrated solution. And here we can see an example of that, where we have a red blood cell that is in solution. In this case, let me indicate for you that red blood cells and body cells in general have a osmotic concentration, a total concentration of salts of about 1%. So 1%, I'm going to put solutes. If it's 1% solutes, then it's 99% solvent, and the solvent is water, so 99% water. If we put such a cell into a solution of distilled water. Do you know what distilled means? Distilled means that we have heated water up to where it boiled, and then we allowed it to condense in a condensation tube, and we collected it. It's pure water. So distilled water is 100% water. And so 100% water, it has more water than 99% water, and water will move in, as indicated by these arrows, and it will cause the cell to swell up. The second possibility here is that the cell is placed in a concentration that is hypertonic to the cell. And notice the terminology they're using here. I do want to comment on that. In this first scenario here, they say the external solution is hypotonic to the cytosol. Cytosol is cytoplasm, and hypotonic means less concentrated, so we use distilled water there. In the second scenario, the osmotic concentration of the cell is still 1% solutes, meaning it's still 99% H2O. And that means the solution out here, they say the solution is hypertonic. Now, the thing with these terms, hypotonic, hypertonic, is we name them according to the solutes in the solution. And remember, the solution is water in the case of osmosis. But the tricky part is that the solutes don't move. It is the solution that moves. And so really we care about the concentration of the solution a great deal here. Of course, it is determined by the concentration of the solutes, but typically we focus on the solutes, but not in the case of osmosis. We concentrate on the solvent, which is water. In this case, we say the external solution is hypertonic to the cytosol. Say, since we could say that it's 10% solutes out here, so 10% solutes would mean 90% H2O. And of course, we can see that 99% inside the cell is more concentrated than 90% outside. And so the water will move from an area of greater concentration of water inside the cell to outside the cell, and the cell will shrivel. The third scenario shows us an isotonic solution, and of course, if the cell is 1% solutes and 99% water, then an isotonic solution will be 1% solutes and 99% water. And this is exactly what you want for an IV. An IV is an intravenous solution. That is, this is how medication can be delivered into a vein. You've seen these little bottles hanging from a rack in a hospital, and that's an IV solution. And the concentration of it should be isotonic. And sometimes if an error is made and the solution is too concentrated, it can be very, very harmful. It can even be fatal. Now, these terms can also be applied in other cases. This is just an animation showing the one case that we saw. In this case, we're placing the cell into a hypotonic solution, into distilled water. And what happens in this case, of course, is the cell swells. In this case, the cell bursts, and this is called plasmolysis. Oops. And this also works on organisms. Let's consider fishes. And we can go here to the next scenario. And we're going to look at a pen. And I want to also change my ink color, so just bear with me here so we can use black ink. So let's consider a fish. In this case, we're first going to consider a fish, a marine fish. And a marine fish is made out of cells that are approximately, it's a happy fish, so about 1% solutes, which means it's 99% water. That's the same concentration as your body, about. Roughly. We're speaking roughly here. And then the ocean is roughly, again, 10% solutes. That's a U, solutes, and 90% water. In this case, let's describe the ocean relative to the fish and the fish relative to the ocean. Remember, when we're using the terms hypertonic, hypotonic, isotonic, that it's the solutes that matters. And so which one is more concentrated? In this case, we would say that the ocean is hypertonic to the fish, and the fish is hypotonic to the ocean. And which way is water going to move? Well, let's first of all consider the fact that water is going to leave the fish. So we're going to have water leaving the fish, but it's not going to leave through the body walls as I'm drawing these arrows here. This isn't going to happen. Here, I'll cross those out, because the body wall is impermeable to exchange, and the area of vulnerability for exchange is the gill. The gills are where the fish breathes, and this is how it gets oxygen. These are organs of exchange, and therefore water can freely leave the fish there, and it does. And so it leaves like crazy. And so to compensate, the fish drinks all the time. So a marine fish in a hypertonic environment drinks like a fish. Now, if you or I drink salt water, we'd have a lot of trouble, but this fish has salt glands, something to keep in mind, that actively remove the salt. If you drink salt water, say you're in a lifeboat or something like that, and you didn't have any fresh water, and you drink salt water, it would go into your stomach, and because it's more concentrated, it will pull water out of your already desiccated or dried cells into your stomach and make you vomit, and you'd lose more water, and it would end up being much more harmful, probably killing you, as opposed to helping you. So you shouldn't drink salt water in a survival situation, even though a saltwater fish can, because of those salt glands. Now, a freshwater fish, so I'm going to draw a line here, and I'm going to put freshwater fish. Its body is very similar to a saltwater fish. It has a solution that's about 1% solutes and 99% water. Now, the difference here is the environment. We call freshwater fresh. It has varying amounts of solutes, but they're very, very small concentration, far less than 1%. So we might say 0.01 or something like that. Or we couldn't just say, let's just say 0.1 to make the math easier. 0.1 solutes is 99.9% water. and we can see that there's more water in the environment. So we would say that the fresh water is hypotonic to the fish, and the fish is hypertonic to the water. And in this case, the water would move from an area of greater concentration to an area of lesser concentration, again to the gills, and this fish would blow up like a water balloon left on a tap and pop, except for one thing. This fish emits a constant stream of dilute urine, constantly urinates. And so if you look at the fish in the room in the aquarium, those fish are almost always urinating, but it's a very dilute stream of urine. And this shows you how these terms apply to fishes in the real world. And that's going to conclude our discussion of osmosis. Make sure you see, as well as my scratchy drawings here, the more sophisticated figure which appears on this slide when you look on the slideshow and not at the video, not at this recorded video. And that's going to conclude